Guys, now the necessity of us having to be able to do this is, I think I've shown you pictures of some of the graphs that we're going to draw. We're actually going to sometimes have like skew asymptotes, like an asymptote that's not just x equals 2 or y equals 1, for example. We can have an asymptote that say y equals x, all right? So we call those oblique asymptotes. So whatever this is, that is either going to be your horizontal asymptote or your oblique asymptote. Oh, sorry, that's frozen, yes. Okay, I circled the Lx. Okay, that whatever that expression is, the part that's not in the fraction, that is going to be your asymptote. So we're going to do a lot of practice in that, but obviously first I just need to actually show you how to go from a fraction to a whole number or an expression plus then a fraction. Okay, so what we're going to do for this example, just write that in there. We're actually going to try and write the numerator as an expression of the denominator, which might not make sense now, but hopefully when I show you how to do that, it will. Okay, so if we have that 2x plus 7 over x plus 5, we need to try and rewrite the numerator so that we have x plus 5 in the numerator as well, so that we can eventually cancel the numerator and the denominator out in certain parts of the numerator. Okay, so if we look at this, you're always going to look at your first term of the numerator. It's 2x. Do we agree that that is the same as 2 times x? Okay, so we're going to do this. We're going to say 2 times x, but what we actually want is an x plus 5. So we're doing some manipulation here. Because if we have 2x plus 5 over x plus 5, the x plus 5s will cancel out and we'll just be left with 2. Okay? But if I multiply this out, is it going to give me the same thing that I had originally? It's going to give me 2x plus 10. I need 2x plus 7. So what must I do if I have 2x plus 10 to get 2x plus 7? I need to minus 3. So do we now agree that we actually have the same thing on both sides of this equal sign, right? But what I can do now, and this is a step that you don't actually have to show, but I am going to show it just because it's the first example. We know we're actually going to put brackets around the x plus 5. Now we're saying that we have one term in our denominator. Okay, technically it's 2 terms, but if I put brackets around it, it turns into 1 term. And now what can you do? If you have more than 1 term in the numerator and 1 term in the denominator, you can split the fraction up. Okay, so that's actually what we're going to do. We're going to say that we have that first term, which is 2 times x plus 5 over x plus 5. You can put the brackets there again, or you don't have to. It doesn't matter really. And then minus 3 over x plus 5. See, and what happens now is we can cancel out those x plus 5s, and I'm left with 2 minus 3 over x plus 5. Okay, does that make sense, guys? So now if we were to actually draw this graph, then our horizontal asymptote would have been y equals 2. Okay, which we are going to do a lot more practice on. We're going to write a note on asymptote, so we are going to summarize all of that. Okay. And guys, doesn't this look like a hyperbola equation? If we look at that, the equation of a hyperbola, if we wrote it like this, if we said y equals, obviously it's not written as y equals now, but we are going to get to that. And we wrote the fraction term first. That's a hyperbola, right? What are my asymptotes here? X equals -5 and y equals 2. So guys, it has actually happened in a core final exam a couple of years ago. I can't remember now exactly, where they gave a graph written in this form or an equation, and they asked them to draw the graph, and it was like the problem solving question. All right. And very few people got it because they weren't understanding how to actually go from this to this form. Okay, so yeah, if you get something like that, you might not, but you never know. Okay, then this is actually a hyperbola. Again, we're going to do examples where we actually draw them. Okay, for now, we're just practicing how to write them. Okay, so I did the working there. We're doing another example, please. That's the next one. Okay, now guys, how this works is that your final fraction, the numerator is supposed to just be a number. Okay, so you're supposed to keep simplifying until you end up with however many terms. It can be more than one term in this first spot here, but then whatever is in your numerator of the fraction that's left has to be a number. Okay, we are later on going to do specific examples where you can't simplify it that far. Okay, but generally that is what we're trying to aim for. Okay, so we have 2x squared plus 10x plus 3 over x plus 5, and we want to write it like this. Okay, I'm just going to rewrite this function quickly. Okay, now if our first term is 2x squared, what do you guys think I need to do in order to bring the x plus 5 into that? What am I going to write in front of the x plus 5? Remember in the previous one, we wrote a 2 in front of the x plus 5 because we had a 2x and we needed 2x when we multiply it out. So now I'm going to do a 2x, yes, times x plus 5. And now we need to fix whatever we've introduced. Okay, so if you want, guys, you can actually do a little tick once you've made sure that it is actually equal to that. So now if we multiply the 2x by x, we do get that 2x squared. Okay, so our first term is the same. But what do I get if I say 2x times 5? 10x. Okay, that actually also works in this case. This is a bit of a silly example then. And then what's left? Plus 3. Okay, you are going to do some now where you might have to do a second bracket. I think I'll do one with you just to show you. And that is then over x plus 5. Now, guys, this step here, which I said previously, you don't actually have to write. You don't have to. Okay, you won't lose a mark if you don't. You can just say, okay, if I put 2x, x plus 5 over x plus 5, what's going to be left? 2x, and then plus 3 over x plus 5. Now, in this case, your asymptote is actually going to be y equals 2x, right? Which is like a straight line, like what we taught you to draw, sorry, in grade 9. Okay, so this one has an oblique asymptote. Again, we'll write a whole note on that. Okay, let's do another example quickly. It is actually the first question from the exercise. So, no, it's not the first one. Let's do the, no, let's do B. Okay. So I just want to write it down quickly. I have a frog in my throat again. Okay, so this is then example 3. Okay, so now again, we're going to just rewrite this, x squared minus 5x minus 3 over x minus 1. Then we look at our first term that we have in the numerator, and we actually also looking at the first term of the denominator, all right? What must I put in front of the bracket if I'm going to have an x plus 1, x minus 1, sorry, in my bracket, and I must multiply it out to get x squared, x. Okay, now let's see, the first term is the same, hey, because x times x is x squared, so that one is fine. What do I get if I multiply this out? I get negative x. I need negative 5x, so I need to do a negative 4x, but now look at what I'm doing. Remember, in the fraction that we're left with, we can't have an x, so I can't just say negative 4x over x minus 1. All right, I actually need to do negative 4x like this. All right, now is my x term sorted, guys. Let's just double check. We have x times negative 1 is negative x, and then we have negative 4x, which does give me negative 5x. Okay, so that's what I meant by saying you can do ticks just once you're certain that one is fine. Okay, now what do we have here? Negative 4 times negative 1 is plus 4, and we need a negative 3. So what must I do to plus 4 to get to negative 3? Minus 7. Now I don't have to put another x minus 1 because I don't actually have a 7x. Well, I don't have more x terms. Okay, and that is then over x minus 1. Okay, now guys, if we look at our first term, what's going to be left? If I were to split this fraction up, x, then second term, minus 4, and then minus 7 over x minus 1. So now your y asymptote is actually going to be y equals x minus 4, which is also a skew line, an oblique asymptote, we call it. Okay. Right, guys, I just want you to try this one on your own quickly, and then we're going to move on. Okay, try that one on your own, please. Okay, let's take a look. Here we go. All right, so 2x squared plus x plus 5 plus 9 over x minus 2. So what I did, do we all agree that it has to be 2x squared, right? In order to, when you multiply it, and you need 2x cubed. Okay, so if we have 2x squared times x, we do get 2x cubed, so our first term is sorted out. Okay, then 2x squared times negative 2 is negative 4x squared. We need negative 3x squared, so we need a plus x squared. Okay, so I write it in that way, an x times x instead of just plus x squared. Okay, so when we do our x times x squared, we do end up with our x squared term. Then x times negative 2 is negative 2x. We need positive 3x, so we need to add a plus, no, not add a plus, but basically we need to plus 5x, which I write as 5 times x. Okay, so that sorts out my 3x there. And now what do I have in terms of just the constant term here? 5 times negative 2 is negative 10, and we need negative 1. So I need to add 9. Then that one is also sorted. Okay, you guys are going to get lots more practice of doing this when we actually get to drawing graphs as well. Yes? Yeah, so we won't be drawing graphs like this. Yes. No, you don't have to worry about having a parabola as an asymptote. Okay, that is not in the AP syllabus. You might do it at varsity, I don't know. I don't remember ever doing it. Okay, we're fine with that though, just the process of simplifying it. Okay, like I said, you are going to get more practice in this later on. Okay, let's do a little, what's the word? Summary of what you must do when sketching a rational function. Because now that you have learned how to do that manipulation, we can start working with actual functions. Okay, so that's quite a long summary. Just copy that down, please, and then we'll go through it. And then we're going to do a separate note on asymptotes, okay, and summarize the different types. So guys, I think most of this isn't foreign to you, right? We've done y-intercepts of any function. You make x equal to 0. To get the x-intercept of any function, you would make the whole function equal to 0 and then solve for x. But now, because remember, we're working with a rational function, okay, the numerator or the denominator is not going to have any influence on what your x-intercepts are. Okay, so you'll see when we do examples, you can actually just take the numerator, factorize that, and then solve for x once y is equal to 0. Then this asymptotes thing, that is what we're going to do a separate note on now, but we did discuss it a little bit. Okay, so now guys, that is just one way of doing it. Okay, I'm going to show you other methods, because sometimes writing the function in that form takes a bit long, or you might have to do some multiplying out. It might be easier to just use another method. Okay, so we're going to do it. We're going to look at different methods. That's one way of doing it, where we write the function in the form that we just practiced. Okay, then whatever the qx part is, whether that's just a number or an x plus 2 or whatever, that is either your horizontal or your oblique asymptote. Now guys, if it's just a number, it's going to be a horizontal asymptote, because that's going to be like y equals 2, okay, which we know is horizontal. It just cuts the y-axis at 2 and it's parallel to the x-axis. But if it's like an x plus 2, then it's an actual oblique asymptote. Okay, oblique is just the same as skew. Then, like when we looked at this example, to show you again quickly, this first one where we said that this is actually a hyperbola. Okay, so the 0 of that denominator is our x asymptote, which is our vertical asymptote, right? So x equals -5. So that's what the second part of that summary means, that the 0 of d of x is the vertical asymptote. Okay, the 0 of whatever you have as your denominator. In some cases, it will just be the 0 of the actual denominator as it's given. All right, we'll look at that now. Stationary points, turning points, how do we find that? We make the derivative equal to 0 and then solve for x. Now this, if required, is referring to the point of inflection. Okay, remember they don't always ask you to find the point of inflection. And like we discussed 2 weeks ago, sometimes the turning point is a point of inflection, all right, that whole thing. But points of inflection are you only need to indicate them if they actually are the same as a turning point, or if they're asking for them specifically. And then, like we said 2 weeks ago, if you have a bunch of points, but you don't actually know how the graph looks, you can look at the signs of f, the signs of the derivative, the signs of possibly the second derivative to figure out the concavity. Okay, we are going to do some practice in that as well. And that can help you to actually figure out what the graph is going to look like. Okay, Now we're going to do a separate note on asymptotes. So you can copy that part down. And this is now the actual like proper definition of a vertical asymptote. So you can just copy that down. It sounds more complicated than it is, okay? So vertical asymptotes exist at the zeros of the denominator where the limit does not exist. Okay, now guys, if we're looking at this first example, we are just going to do two so that I can show you the two different types. For this first example, what is the zero of this denominator? Which x value would make this denominator equal to 0? 2. Does the limit of this function exist as we're tending to 2? Let's write that down quickly. The limit as x tends to 2. Because what is this definition saying? Vertical asymptotes exist at the zeros of the denominator where the limit does not exist. Okay, so the limit to that specific 0, that x value. Then of this function, we have x over x minus 2. Now, guys, if I sub in 2 there, or let me first ask, can I simplify that function somehow so that when I sub in 2, my denominator is not equal to 0? No, okay, I can't factorize there, nothing. So here, this limit does not exist. So it is the 0 of the denominator and the limit does not exist at that value. Okay, so therefore, we are going to have a vertical asymptote at x equals 2. But what if we have something like this? Let's call it g of x. Do we notice that this function now has, or the denominator of this function rather, has 2 zeros? We used to refer to them as critical values, right? X equals -2 and x equals -3. So now we need to check, does the limit not exist at both of those values? Because then we're going to have 2 vertical asymptotes. All right, what do we notice? The x plus 2's can cancel out. But what would that make x equals -2 then on the actual graph when we're drawing it? A removable discontinuity, do you guys remember? So you're just going to have like a hole at x equals -2 at that point. Okay, so in this case, you can't just say because -2 is a 0 of the denominator, it's going to be a vertical asymptote. All right, because the x plus 2's can cancel each other out, it is going to be a removable discontinuity and not actually an asymptote. Okay, how to prove that? If we have the limit as x tends to -2, let's actually then just simplify this. All right, it's actually going to be 1 over x plus 3. If we simplify the function. You can also add it there on the side if you want. But remember, when you simplify it, you do actually have to just state that x cannot be equal to -2. Okay. Now, does this limit exist, guys? Can I sub in -2 there? Yes, and it will actually give me a value, hey? It's going to be 1 over -2 plus 3, which is also 1. So this limit is 1. So it is a 0 of the denominator, but the limit does actually have a value. It does exist as we tend towards that point. Okay, so here we have no vertical asymptote at x equals -2. And let's then just put in brackets, it's actually going to be a removable discontinuity. Then the other one, let's just write it down so that we have the full working here. So if we look at the other 0 of the denominator, which is -3, and we can use our simplified function here. Right, we can't simplify that fraction in any way so that the x plus 3 is not like a problem really. So this limit does not exist because if we sub -3 in there, the denominator is 0. So therefore, we are actually going to have a vertical asymptote at x equals -3. Now, guys, you don't have to write all of that down if you can actually just kind of reason it out, okay? Unless they specifically ask you. They might ask you, is there a vertical asymptote at x equals -2? Justify your answer or something like that. Then you need to know that this is how you would do that, okay? So you do actually have to kind of know that definition and be able to apply it. So guys, in these two cases, we didn't actually have to write the function in that form. We have a whole number or expression plus a fraction in order to get the vertical asymptotes. Okay, but you would possibly have to do it to get the others. I'm not going to write that down now. Okay, this part is just on vertical asymptotes. We're going to do one now on the other two types. Okay, are we fine with this? Just finding the vertical asymptote. Okay, next one is horizontal asymptotes. Okay, so number 2, yes?
Basically, it's the vertical asymptote wherever the jump is.
It's wherever. I don't want you to remember it like that. I want you to actually remember it as the zeros of your denominator. But if you can cancel one of them out, then not. Yeah. But where you have a jump discontinuity, you're not always going to have an asymptote, if that makes sense. Yeah, it could, but it could also have 2 holes. Then it's also a jump discontinuity. Okay. All right, next one, horizontal asymptote. Okay, so we're just going to write that. If we have a function which is a rational function, so I'm just going to write it as g of x over h of x to show that it is a fraction. Now, guys, you saw in the examples where we changed the way that the function was written, that sometimes you have a horizontal asymptote, sometimes you have an oblique asymptote, all right? But the method of getting it is technically the same. So there will be a horizontal asymptote if the degree of g of x, so the degree of the numerator, right, is smaller than or equal to the degree of the denominator, so the degree of h of x. That's just a way of knowing when you're looking at the actual function whether there will be a horizontal asymptote or an oblique asymptote. Okay, now we can just quickly look at the examples that we actually did, just so that it's cemented a bit. Just going to read through this again. If you have a rational function, there will be a horizontal asymptote, not an oblique asymptote. Okay, it's always going to be one or the other. You won't have both. Okay, you can have a vertical one, yeah, sorry, and horizontal or and oblique, but not horizontal and oblique. Okay, so there will be a horizontal asymptote if the degree of the numerator is either the same as the degree of the denominator or smaller than the degree of the denominator. Okay, so if we're looking at these examples that we did, in the first one, do we notice that we have the same degree at the top and the bottom? Right, so according to that definition now, there should be a horizontal asymptote. You see when we wrote it like this, we're getting a horizontal asymptote, y equals 2. Okay, for the next one, now this degree is bigger than the degree of the numerator, is bigger than the degree of the denominator. And are we getting a horizontal asymptote, 2x? No, we're getting a oblique one, an oblique one. Right, same thing here. We didn't do this example, but this was the first question in the exercise. Same degree at the top and the bottom, so the degrees are equal, so we should get a horizontal asymptote. Okay, we did this one. Degree here is bigger than the degree at the bottom, so we're getting an oblique. Next one, degree bigger again. So now we're getting a parabolic, I suppose, which is not in the syllabus, but it's not a horizontal asymptote, right? Because the degree of the numerator is not smaller than or equal to the degree of the denominator. Okay, which is what that is saying. So now, guys, for horizontal asymptote, if you're looking at your function and you're seeing, okay, the degree of the numerator is smaller than or equal to the degree of the denominator, so I know there has to be a horizontal asymptote, not an oblique one. Then there are two methods in which you can find that horizontal asymptote. Okay, so the first method is, let me just get back to my note here. Then, now we're going to work with limits again, which you might be happy about, you might not, I'm not sure. The line y equals c is a horizontal asymptote of f of x if the limit as x tends to positive or negative infinity, but we usually just work with positive infinity, I'll show you, of that function is equal to c. So what that is basically saying, I've used the proper wording of the kind of rule, but it's basically saying if you're figuring out, or if you have already figured out that there will be a horizontal asymptote, then the limit as x tends to infinity of that function will give you the horizontal asymptote. Okay, it will give you a number, a specific value, and that specific value will then be the actual equation of the asymptote. Or if you don't want to do that, some of you might prefer this. You can do what I showed you before, the line y equals now q of x, but q of x in this case will be a number, is a horizontal asymptote if f of x is written in this form. And now, guys, in the examples that we did, we wrote it as Lx plus Px over Qx, but those letters aren't actually fixed. They can use any letters, all right? So I just wanted to show you that as well. So if you're writing in that form, a function plus the simplest form of the fraction there at the back, then that will be a number, and that number will be the horizontal asymptote. Okay, so you can decide, do you want to do the limit as x tends to infinity? I don't think that's very hard. Okay, well, you did it now for your test as well, or you can write it in that form and then just say that number. Okay, let's quickly do some examples here. We were just practicing this limit thing again, just to remind you of how to do that. If we have f of x equal to x over 2x plus 1, and we're not going to worry about the vertical asymptote now. All right, we're just discussing the horizontal. Now, guys, in this case, do we see that the degree of the numerator is the same as the degree of the denominator? So we know that definitely we are going to have a horizontal asymptote, not an oblique asymptote. Now, guys, this is going to be quite difficult if you try to write it in that form, hey? Because you have an x at the top and a 2x at the bottom. So, I mean, you can write a half bracket 2x plus 1. Right? Do you see what I'm saying? But I don't think we really want to be working with fractions. It would be fine if you did that, okay? You would still get to the same answer. But let's practice doing this limit thing. All right, so first we figure out we're going to have a limit, sorry, not a limit, a horizontal asymptote. So let's do the limit. So limit as x tends to infinity of x over 2x plus 1. Okay, now the way that I do it, I know Mrs. Race showed you guys some kind of shortcut, but from marking, I think most people did it using this method, where you look at the highest degree of x that you have, and you then divide each term by that. So here we just have x as our highest degree. If you want to use a shortcut, that's fine. You'll still get all the marks. I actually was never taught the shortcut, so I've just never used it. That's what I'm saying. I actually don't know what it is. It's in her notes that she posted last year. But I think if this one works for you, then just do this. Is this the shortcut? Yeah, it has conditions, which I don't really like. I like just having a kind of a one-size-fits-all approach. Okay, now guys, this step you don't actually have to show, all right? You can just do the dividing by x in your head, but I'm just showing it again, just to revise. So x over x is obviously, oh, I left out my limit. Rookie error. There we go. Sorry, I'm still in long weekend mode. Please write that limit there. Okay. Actually did that on purpose just to remind you guys that you can sometimes forget that step. Okay, so what am I left with at the top? Let's just do limit first before we forget again. So limit as x tends to infinity. We have 1 at the top over 2 plus 1 over x. And now if we think of 1 over x, all right, whenever that tends to infinity, it's going to tend to 0, essentially. So what am I left with? 1 over 2. So that means that we're going to have a horizontal asymptote at y equals a half. Okay. Now guys, if you have a function where the degree of the numerator is bigger than the degree of the denominator, and you try to do this, you try to find the limit as x tends to infinity, you will see that it actually does not exist. So I'll just show you quickly. I'm not going to write that down now. This, for example, we see that the degree here is bigger than in the denominator. Oh, I'm fumbling over my words today. Okay, so maybe you don't realize that you're not going to have a horizontal asymptote. Maybe you forget that, and then you try and find the limit as x tends to infinity. What is the highest degree of x now that I have here? X squared. So now we need to divide each term by x squared, all right? So x squared over x squared is 1 plus 3 over x squared. Then here we're going to have x over x squared, which simplifies to 1 over x, and then minus 1 over x squared, which is that. Now, guys, do we notice that for both of these terms in the denominator, it's over an x or an x squared? So when I now make that tend to infinity, I'm going to get 0 for both of them in my denominator. All right, so that means that this limit does not exist. So I don't have a horizontal asymptote. I am, in fact, going to have an oblique asymptote. Okay, so that is the next part. Sorry, are you copying that down? You don't have to. No, it's fine. Just check how we're doing for time. Oh, almost done. Let's just copy this last bit down. Okay, so 3. an oblique asymptote, which is always of that form. It's a straight line, y equals mx plus c. Like I said, parabolic or whatever, that's not in the syllabus, so don't worry about that. So if, and again, we have a function which is a rational function. So we're just going to write that as g over h. There will be an oblique asymptote. I'm just going to abbreviate asymptote like that. If, and this is now very specifically, only if the degree of the numerator is 1 more than the degree of the denominator. Okay, so if the degree of g is equal to the degree of h plus 1. And now if that is the case, guys, the only way of finding the equation of the oblique asymptote is to rewrite the function into the form that we practiced at the beginning of the lesson. Right, and then whatever is not in that fraction is your oblique asymptote. So then the line y equals qx is and now I'm just going to use OA for oblique asymptote. If f of x is rewritten in that form.
When we
Yeah.
rewrite it, should we like write that first? It's kind of like
This, no, you don't have to. You can if you want, if it will help you. But you don't have to. Okay, now guys, you can see that there are kind of different combinations of what you can do here. If you're getting your function right from the start and you're writing it in this form right from the start, okay, then you would actually be able to see all of your asymptotes from that form. Because whatever your qx is, if it's just a number, that's your horizontal asymptote. If it's an expression with an x in it, then it's going to be an oblique asymptote. And then whatever the zero of this denominator is, will be your vertical asymptote, all right? But if it's given in a form like, for example, this example that we did here, right here, if you wanted to rewrite this function in that form, you would first have to multiply the brackets out and do some working. Okay, so it actually is up to you guys. We are going to do some examples. I think we'll carry on with AP this afternoon, right? I'm seeing you guys again at 3:15. So we'll carry on with this. We'll find some asymptotes. We'll practice actually doing it, finding all of the asymptotes of a function, and then we're going to start drawing them as well. Okay, then tomorrow what we'll do is we'll do core in both sessions. Okay, so guys, sorry that it's different from the list that I've sent you. We are going to kind of mix and match depending on where we are. So I'll tell you what we're doing in which session. Okay.
I wasn't sure we got this lab. I was thinking, is there like a memo that
I can't remember that we haven't actually looked at it properly. We need to make some time to look at it properly. Yeah. Okay.
I'm not gonna be
This afternoon. Oh, okay, that's fine. You'll do, you'll do something catch up on what you missed. Okay.
I'm also, so I'm sorry, I'm not gonna be able to take this.
Okay, that's fine. Just like what I said. Okay. All right, guys. Thank you. See you later. Bye. Yeah.